Is light composed of particles or waves? This simple question sparked the genius of Albert Einstein and led him to win the Nobel Prize in Physics in 1921. This is a video explaining how this simple question led Einstein to revolutionize quantum mechanics. It is the story of the photoelectric effect. The story begins with the ancient Greeks pondering the nature of the universe. Is the universe composed of particles, or does it bear more resemblance to a wave? If both concepts are indeed accurate, what occurs when they intersect? In the 5th century BCE, Democritus, a Greek natural philosopher from Abdera, proposed a theory of atomism. He suggested that everything is composed of tiny, indivisible particles known as atoms. The term atoms signifies indivisibility. These atoms, in constant motion, traverse through space and combine to form matter. However, Plato, another influential Greek philosopher, held a contrasting view. He expressed skepticism towards Democritus' atomic theory. Plato believed that reality was predominantly influenced by waves rather than particles. This created ongoing discussions among philosophers. Some believed the universe was made up of waves, while others thought it was made of particles. Philosophers following the Pythagorean teachings suggested that every visible object continuously releases tiny particles. On the other hand, Aristotle thought that light moves like waves in the ocean. To make it easier to understand, let's imagine it this way. Democritus believed the universe was similar to a Lego set. Just as a Lego set consists of many tiny blocks, he proposed that the universe was composed of tiny, indivisible particles called atoms. Conversely, other ancient Greeks perceived the universe as a single, unchanging entity. This viewpoint is akin to seeing an entire Lego set as one large, unalterable piece. Fast-forwarding to the 17th century, René Descartes, a philosopher and physicist from France, made significant contributions to the field of optics. He postulated that light is a mechanical property, implying that he considered light as a physical entity originating from a source such as a lamp or the sun, and propagating through a medium like air or water. Descartes also proposed a theory explaining how light bends, or refracts, when transitioning from one medium to another. Contrary to what we observe, he believed that light travels faster in denser mediums. Pierre Gassendi, an atomist, suggested that light is made up of particles. This theory was later studied and favored by Isaac Newton, one of the greatest physicists of mankind. In 1675, Newton hypothesized that light is composed of particles, or corpuscles, emitted from a source in all directions. He argued against the wave nature of light, stating that unlike waves, which can bend around obstacles, light travels in straight lines. In this theory, he explained phenomena like reflection and refraction. However, it fell short when it came to explaining phenomena that involve the wave-like behavior of light, such as diffraction, polarization, and interference. In 1665, Robert Hooke developed a pulse theory to elucidate the origin of colors. He compared the propagation of light to the spreading of waves in water in his work, Micrographia. Later, in 1672, he suggested that the vibrations of light could move perpendicular to the direction of propagation. In 1678, the Dutch physicist Christian Huygens developed a mathematical wave theory of light and published it in his treatise on light in 1690. He proposed that light radiates in all directions as waves, and believed that these waves decelerate when they enter a denser medium, such as moving from air into water. This theory suggests that light behaves like waves. Around 1800, Thomas Young demonstrated that light waves could interfere with each other, similar to sound waves. He also suggested that different colors are caused by different wavelengths of light. This theory was able to explain phenomena that Newton's corpuscular theory could not. Another supporter of wave theory was Leonhard Euler. He argued in Nova Theoria Lucis et Calorum in 1746 that diffraction could be better explained by it. In 1816, André Marie Ampère gave Fresnel the idea that the polarization of light could be explained by the wave theory if light were a transverse wave. Later, Fresnel independently worked out his own wave theory of light. By 1821, Fresnel was able to show via mathematical methods that polarization could be explained by the wave theory of light if and only if light was entirely transverse, with no longitudinal vibration whatsoever. The wave theory of light faced a significant challenge due to its assumption that light waves, like sound waves, needed a medium to travel through. This medium was thought to be a hypothetical substance called luminiferous ether, first proposed by Christian Huygens in 1678. According to this theory, light waves were believed to propagate through this ether, similar to how sound waves travel through air. However, in the late 19th century, the Michelson-Morley experiment was conducted to detect the movement of the Earth through this ether. The outcome of the experiment challenged the validity of the luminiferous ether theory and undermined the wave theory of light's reliance on a medium for transmission. Newton's theory suggested that light would travel faster in a denser medium, while the wave theory suggested the opposite. It wasn't until 1850, when Léon Foucault made an accurate measurement of the speed of light, that the wave theory was supported and the particle theory was largely abandoned. In 1845, Michael Faraday made a significant discovery known as the Faraday rotation. He found that the direction of vibration of light can be rotated when light travels through a transparent material along a magnetic field. This discovery was crucial because it suggested a connection between light and electromagnetism. Faraday proposed that light could be a form of electromagnetic disturbance, a high-frequency vibration traveling along magnetic field lines. Importantly, Faraday's insights challenged the prevailing notion of luminiferous ether as a necessary medium for light transmission. He suggested that light could propagate through empty space, indicating that it might be an electromagnetic wave capable of traveling without a medium. Inspired by Michael Faraday's work, James Clerk Maxwell delved into the study of electromagnetic radiation and light. Through his research, Maxwell discovered that electromagnetic waves could propagate through space at a constant speed, which was the same as the speed of light. This led Maxwell to conclude that light itself was a type of electromagnetic wave. Maxwell initially presented this groundbreaking idea in 1862 in his paper titled On Physical Lines of Force. Subsequently, in 1873, Maxwell published his seminal work, titled A Treatise on Electricity and Magnetism, which provided a comprehensive mathematical framework describing the behavior of electric and magnetic fields. This body of work, now famously known as Maxwell's equations, offered a profound synthesis of electromagnetism and optics, firmly establishing the connection between light and electromagnetic waves. Heinrich Hertz confirmed Maxwell's theory by creating and detecting radio waves in a lab and showing that they behaved just like light, with properties like reflection, refraction, diffraction, and interference. Since the 1860s, scientists have been exploring what happens when both wave and particle theories intersect by analyzing what is called blackbody radiation. This is something we can observe in everyday life. For instance, if you put a piece of iron in a fire, you will notice that it changes color as it gets hotter. It starts off radiating red light, then, as it heats up, it turns orange, then white, and finally blue at very high temperatures. To investigate this phenomenon, a German scientist named Gustav Kirchhoff and his colleagues conducted an experiment. They took a closed metal box and made a tiny hole in it to let some light escape. This box is what we call a black body. They heated the box and observed the light that came out of the hole. They then measured the wavelengths of light coming out of the hole. Light, which is a type of wave, has a property called wavelength. This wavelength of light determines its color. Short wavelengths correspond to blue light, and long wavelengths correspond to red light. They found that the pattern of light wavelengths depended only on the temperature of the black body. It did not matter what material the box was made of or the shape of the box. This was a big problem back then. According to the classical physics rule, also known as the Rayleigh-Jeans law, the intensity of light should increase infinitely with decreasing wavelength. However, this prediction didn't match the experimental observations made by Kirchhoff and his colleagues, leading to what was known as the ultraviolet catastrophe. At that time, nobody could completely explain the mathematical formula that would result in the hill-like pattern seen in these graphs. After Kirchhoff passed away in 1887, the task of investigating black body radiation was taken up by another brilliant scientist named Max Planck, who is also known as the father of quantum mechanics. Planck was born in 1858 into a family in Germany that was known for being really smart. He was a well-dressed, proud German who was a bit shy. He was known for his determination, traditional values, and formal behavior. He was also conservative in his views. Due to his conservatism, he was initially skeptical about atomic theory. He preferred the concept of continuous matter over discrete particles. As he wrote in 1882, despite the great success that the atomic theory has so far enjoyed, ultimately it will have to be abandoned in favor of the assumption of continuous matter. In 1900, Max Planck devised a formula, which he referred to as a fortuitous guess. He wasn't certain it would work, but he tried it nonetheless. This formula could explain how the color of light changes as things heat up. Initially, Planck was not fond of the methods used by another scientist named Ludwig Boltzmann. However, he later had to concede that Boltzmann was correct. There was something peculiar about Planck's formula, though. It only worked if he included a very tiny number, about 6.62 times 10 to the power of negative 34. This minuscule number is now known as Planck's constant, and it's one of the fundamental numbers that scientists use to comprehend the universe. Planck initially didn't grasp the full implications of the constant he discovered. However, he later developed a theory that revolutionized our understanding of light and energy. Planck proposed that objects radiating heat and light contained vibrating particles, which he termed harmonic oscillators. These oscillators could only absorb or emit energy in discrete packets, or quanta. The size of these energy packets was determined by Planck's constant. Planck considered his constant a tool for calculation that explained the process of emitting or absorbing light, but did not apply to the fundamental nature of light itself. In his paper on the law of distribution of energy in the normal spectrum, Planck suggested that the energy carried by electromagnetic waves could only be released in packets of energy. In December 1900, he made a significant declaration to the Berlin Physical Society. We therefore regard this as the most essential point of the entire calculation of energy to be composed of a very definite number of equal finite packages. Apart from figuring out the meaning of Planck's constant, scientists were also puzzled by a phenomenon called the photoelectric effect. This effect occurs when light hits a metal surface, resulting in the emission of electrons. Back in 1887, the German physicist Heinrich Rudolf Hertz discovered the photoelectric effect while working on radio waves. In simple terms, the photoelectric effect is the phenomenon of light causing electricity to flow. He was working with a device that had a coil and a gap where a spark would appear when it detected electromagnetic waves. To see the spark better, Hertz put the device in a dark box. But he noticed something interesting: the spark wasn't as long when the device was in the box. He figured out that this was because a glass panel in the box was absorbing ultraviolet light, which was helping the electrons to jump across the gap and create the spark. When Hertz removed the glass panel, the spark got longer because more UV light could reach the device. But when he replaced the glass with quartz, which doesn't absorb UV light, the spark stayed the same length, just like when he removed the glass panel. This was a discovery in our understanding of the photoelectric effect and the nature of light and electricity. These discoveries by Hertz led to a series of investigations by Wilhelm Hall-Wachs, Augusto Righi, and Alexander Stoltaf. Hall-Wachs conducted an experiment. He shone UV light on a zinc plate. If the plate was negatively charged, it lost its charge. If it had no charge or was positively charged, it became more positive. This means the UV light made the plate release negative particles, which we now call electrons. From these observations, he concluded that some negatively charged particles were emitted by the zinc plate when exposed to ultraviolet light. Between 1886 and 1902, Wilhelm Hallwachs and Philipp Lenard conducted studies on the photoelectric effect, which is when light causes a material to emit electrons. Lenard discovered that when UV light strikes one of two electrodes in a vacuum tube, it generates an electric current. However, when the UV light is turned off, the current also stops. This marked the beginning of our understanding of the photoelectric effect. In 1900, Lenard also discovered that UV light can ionize gases or make them charged. This effect occurred over several centimeters of air and created more positive ions than negative ones. J.J. Thomson interpreted this as the Hertz effect acting on the particles in the gas. In 1902, Philipp Lenard conducted significant experiments related to the photoelectric effect. In these experiments, he used a glass tube fitted with a thin aluminium window, which allowed him to study the radiation outside the tube. An unexpected phenomenon was observed in his experiments. As the frequency of light increased, from infrared heat and red light to violet and ultraviolet, the electrons emitted accelerated with significantly more energy. He then increased the intensity of the light using a carbon arc light, which could be brightened by a factor of 1000. Given that the brighter, more intense light carried substantially more energy, it was logical to anticipate that the emitted electrons would possess more energy and consequently move faster. However, this was not the case. While the more intense light did produce a greater number of electrons, the energy of each electron remained constant. This was a finding that the wave theory of light failed to explain. Einstein had been contemplating the work of Planck and Lenard for 4 years. In his final paper of 1904, on the general molecular theory of heat, he discussed how the average energy of a system of molecules fluctuates. He then applied this theory to a volume filled with radiation. He found that experimental results were comparable. After finding this result, he said, "I believe that this agreement must not be ascribed to chance." In a letter to his friend Konrad Habicht, written shortly after completing the 1904 paper, Einstein expressed, "I have now found in a most simple way the relation between the size of elementary quanta of matter and the wavelengths of radiation." This revelation seemingly prepared him to formulate a theory that the radiation field was composed of quanta. Einstein did exactly that. He applied Planck's mathematical discoveries, literally, connecting them with Lenard's photoelectric findings, and examined light as if it were made up of discrete particles, called light quanta, instead of being a continuous wave. On March 17, 1905, he submitted a paper to the Annalen der Physik with a slightly odd title, "On a heuristic point of view concerning the production and transformation of light." Heuristic what? It means a hypothesis that serves as a guide and gives direction for solving a problem but is not considered proven. Einstein's paper started by highlighting the distinction between theories based on particles, such as the kinetic theory of gases, and theories involving continuous functions, like the electromagnetic fields in the wave theory of light. He pointed out a significant formal difference between theories concerning ordinary matter like gases and tangible objects, and Maxwell's theory of electromagnetic phenomena occurring in what was then considered empty space. Einstein noted that while the state of a body is considered to be entirely determined by the positions and velocities of a large, yet finite, number of atoms and electrons, continuous spatial functions are used to describe the electromagnetic state of a given volume. Einstein also emphasized that the particle theory of light would not necessitate the abandonment of the wave theory. It is still useful. He stated that the wave theory of light, which operates with continuous spatial functions, has worked well in the representation of purely optical phenomena, and will probably never be replaced by another theory. The paper proposed a way to reconcile both a wave theory and a particle theory in a heuristic way. It suggested that our observation of waves involves statistical averages of the positions of countless particles. He said that it should be kept in mind that the optical observations refer to time averages rather than instantaneous values. This means that when we observe light, we're not seeing a single moment in time, but an average of many moments. Then came what may be the most revolutionary sentence that Einstein ever wrote. According to the assumption to be considered here, when a light ray is propagated from a point, the energy is not continuously distributed over an increasing space, but consists of a finite number of energy quanta that are localized at points in space, and which can be produced and absorbed only as complete units. In short, light is made up of discrete particles or packets of energy. These groundbreaking ideas emerged from his exploration of whether a volume of black-body radiation, which he now assumed to be composed of discrete quanta, might behave similarly to a volume of gas, which consists of discrete particles. First, he examined the formulas that showed how the entropy of a gas changes when its volume changes. Entropy is simply a measure of disorder or randomness. Then he compared this to how the entropy of black-body radiation changes as its volume changes. He found that the entropy of the radiation varies with volume according to the same law as the entropy of an ideal gas. After discovering this, he did a calculation using Boltzmann's statistical formulas for entropy. The statistical mechanics that described a dilute gas of particles were mathematically the same as those for black-body radiation. This led Einstein to declare that the radiation behaves thermodynamically as if it consisted of mutually independent energy quanta. It also provided a way to calculate the energy of a particle of light at a particular frequency, which turned out to be in accord with what Planck had found. Einstein demonstrated how the existence of these light quanta could explain what he graciously referred to as Leonard's pioneering work on the photoelectric effect. If light came in discrete quanta, then the energy of each one was simply determined by the frequency of the light multiplied by Planck's constant. Einstein suggested, if we assume that a light quantum transfers its entire energy to a single electron, then it follows that light of a higher frequency would cause the electrons to emit more energy. Conversely, increasing the intensity of the light, but not the frequency, would simply mean that more electrons would be emitted, but the energy of each would remain the same. Therefore, if the frequency is not high enough, no electrons will be emitted, regardless of the light's intensity. This was precisely what Leonard had discovered. Einstein's 1905 paper marked a significant leap beyond Planck's work by proposing that light is composed of discrete packets of energy called quanta, or photons. This idea fundamentally challenged classical physics, introducing the concept of quantum mechanics. As Einstein noted in a paper the following year, his role was to figure out the physical significance of what Planck had discovered. Planck initially viewed the quantum as a mathematical tool to describe energy emission and absorption during interactions with matter. But he did not see that it related to a physical reality that was inherent in the nature of light and the electromagnetic field itself. Einstein believed that the concept of the light quantum represented a fundamental aspect of reality. He viewed these energy quanta as existing even when light traveled through a vacuum. Einstein wrote, "We wish to show that Mr. Planck's determination of the elementary quanta is to some extent independent of his theory of black-body radiation." In other words, Einstein argued that the particulate nature of light was a property of the light itself, and not just some description of how the light interacts with matter. Even after Einstein published his paper on light quanta, Planck didn't immediately agree with him. Planck believed that quanta were only involved when light was absorbed or emitted, not when it was freely present in a vacuum. He advised, "I do not seek the meaning of the quantum of action light quantum in the vacuum, but at the site of absorption and emission." This shows the initial resistance in the scientific community to new theories, even those that would later prove revolutionary. Despite his disagreement, Planck proposed Einstein for a prestigious position in the Prussian Academy of Sciences 8 years later. The letter he and other supporters wrote was filled with praise, but Planck added that he might sometimes have overshot the target in his speculations, as for example in his light quantum hypothesis, should not be counted against him too much. Before his death, he wrote, "My futile attempts to fit the elementary quantum of action somehow into classical theory continued for a number of years, and cost me a great deal of effort. Many of my colleagues saw in this something bordering on a tragedy. Albert Einstein's theory of the photoelectric effect was indeed testable experimentally. The crucial experiment was conducted by physicist Robert Millikan. Despite verifying Einstein's photoelectric formulas, Millikan still rejected the theory. He stated, despite the apparently complete success of the Einstein equation, the physical theory on which it was designed to be the symbolic expression is found so untenable that Einstein himself, I believe, no longer holds to it. However, Millikan was mistaken in asserting that Einstein had abandoned his formulation of the photoelectric effect. In fact, it was specifically for his discovery of the law of the photoelectric effect that Einstein was awarded his only Nobel Prize. With the advent of quantum mechanics in the 1920s, the concept of the photon became a fundamental part of physics. If you want to know the history of quantum mechanics, check out our video. The link is provided in the description below. Indeed, Millikan was correct on a broader perspective. Einstein increasingly found the strange implications of quantum theory and the wave-particle duality of light to be profoundly disturbing. In a letter written towards the end of his life to his close friend Michel Basseau, Einstein expressed his ongoing struggle with the concept of light quanta, even after quantum mechanics had been widely accepted by the physics community. He wrote, "All these 50 years of pondering have not brought me any closer to answering the question, what are light quanta?" This reflects Einstein's lifelong quest to understand the fundamental nature of light and its quantum properties. From many experiments, we came to the conclusion that light has a dual nature. The dual nature of light challenged classical physics paradigms and led to the development of quantum mechanics, which has profoundly impacted our understanding of fundamental physics. Quantum mechanics and general relativity are indeed two of the strongest theories that explain most of the phenomena in the universe. However, we can't reconcile them yet. And this is the biggest problem in our modern science. Let's embrace curiosity and imagination to unlock new frontiers of knowledge through scientific discovery.